Hello and welcome to the third lecture in the discussion about ordinary least square regression in chapter 20 of our comprehensive course in AI, ML and DS. Now, previous one was also discussion about OLS, but there the issue which we got was that the R square which we got was very less. As I told you that R square is a measure of how good the line fits with your data points. So if R square is say 0.8, it's good model. 0.85 better model, 0.95 still better model, you will say. But here I got R square 0. That means that my OLS model completely failed to meet the requirements of that OLS regression. And the reason was not the limitation of some kind of OLS model or algorithm, but that is because we are applying a misplaced algorithm, right? Because our data distribution is not at all linear. In fact, it is somewhat circular like this. And we try to force a linear model on that data. So as a result, we got a model which somehow it did its fixing thing, but we got a model with very poor metrics. Okay, still it managed some F statistic of 0.40 or that is 41 around. Okay, that is 41%. But even that is very poor because F statistic also should be reasonably high, 85% or something like that. So this is not at all a good model. But now we want to take example where our data would be more or less linearly distributed. So and now we will slowly do the whole thing in that kind of workflow which is to be done in all subsequent next chapters, right? So first step is always importing the library. So here we are importing NumPy, Matplotlib. These are our well-known thing. From scipy.states we are importing T. What is that T does? That we'll see. Import states-model.api as SM. Okay, this is required, we know, for doing ordinary least square regression. Now we create the data. So first step will always be like this for all subsequent chapters, importing library. Second step would not be data generation, but second step would be importing the data, loading the data, because this is synthetic data which we are generating, but in practice the data will always be given to you in a CSV file or Excel file. So here the step would be data is equal to pd.read_csv, where pd is that pandas, so you will have to import pandas as pd also here, and pd.read_csv, the name of the data.csv file, or pd.read_excel, or maybe parak file, or we have seen how to import different types of data set, how to load the data in the Jupyter environment. So that step would replace these steps. But here we are creating a synthetic data, so this is the normal that is a random seed for reproducibility, and x is equal to np.lean space. So this time we are not taking x and y both random normal, because then we will be again produced with presented with this kind of data. So that would be not a good data set for displaying the great properties of OLS regression. So we are deliberately taking a data which is linearly distributed, 0 to 100 minimal maximum values, and 50 data points will be created. No, then what kind of linear relationship would be we want? Then actually linear relationship is like this: y is equal to beta 0 plus beta 1 into x1, or something like y is equal to 7 plus 5 into x1. Okay, so here we want to do y is equal to 2x plus 10. Y is equal to 2x plus 10. But this extra term needs to be added. Why? Because if you just write y is equal to 2x plus 10, then your y and x would be perfectly linearly related. Perfectly linearly related means your y and x would be like these blue colored dots. So if they are like this blue colored dot, then I can always pass this dotted green colored line, and that is a perfect OLS model, and its R square, that value of R square would be 100% or 1. Okay, but we don't want a perfect model. We want a model which is reasonably good but not perfect, and that means we also don't want a practically linear data set like this, because in a normal data set this was a synthetically generated, so it is possible to generate this kind of data. But for naturally obtained data sets which you will be given, it will always be this kind of data. It will never be these blue dots but these green dots. So that means they will be more or less linear in trend, but y more or less linearly increases as x increases, but not exactly on a straight line, but somewhat disturbance on either side of that straight line that is required, right? So here we are getting that noise np.random.normal between 0, 10, and the size is x.shape. Okay, so then x.shape means I don't want to generate data point somewhere here. I want that my data point should be generated only as long as my x variable is spread. So that is why I have limited the whole limit to size is equal to x dot shape. So my normal distribution of that green points, that should be having size is equal to x dot shape. And I also added 0 to 10 disturbance only, not big disturbance like 0 to 100 or 0 to 80. If I add big disturbance in this manner, then it is clear that it would be again more or less that data set only, that is the earlier data set, this kind of data set only, and then the OLS will not be a good model to select in the first place. Okay, so we are adding some noise so that the points are a little bit scattered with respect to this some kind of dotted line, but the distribution is more or less linear. So this is the linear part, and this noise is just some little bit non-linear part, right? So that we are adding here, And as I will plot the graph, you will come to understand that what is the meaning of this word, why this noise is important. Okay. Now, then these steps. Now, these steps in all data science problem, first step would be importing library, second step would be loading the data or creating the data. Then third step would be selecting the algorithm, right? So you will have to select the algorithm. Now for OLS regression, you have to just select this sm.add underscore constant x. That term is required because otherwise I told you that OLS regression cannot give you this thing. That is the intercept term. It cannot give, right? So you have to manually add that intercept term. And then model is equal to this step. These lines, 3 lines always remain same. So x is equal to sm.add constant small x. Model is equal to sm.ols small y and big X, where small y is what? This. Okay. And big X, here it should be big X. Okay. Now then this model is equal to sm.ols yx. So this is just initializing model, but you have not yet fitted your model on your data set. In fact, this model can be fitted on any data set. But here in my environment at present, this data set is loaded. So y versus x. So it will be fitted on y versus x, this value of y and this value of x, right? So then result is equal to model dot fit. In this step, actually the model fitting is done and the results are collected, and then you will print the output of that result. So previous cell and then this cell. Now you are getting this kind of output. You can see there is a visible improvement. Now R square is 97.5% or 0.975, which is very, very good linear model. Okay. Then F statistic is also very high. Probability of F statistic is very less, 2.81 into e raised to minus 4. Log likelihood is this value. We are going to discuss in detail about this all parameters in this lecture only. So don't worry about what these things are and whether they should be high or low. But you can see this is the constant and this is the slope term. Okay, coefficient of constant is, that is constant itself, that is that beta 0 is 10. You started your data set itself with 10, so obviously it will be 10 only, but a little bit disturbance is created because of that noise term, right? So that noise term that creates the disturbance. And at coefficient of x1. Now what is coefficient of x1? That is this term slope, that is beta 1 into x1. Now in your case, the coefficient of x1 is this 2. Okay, so this is beta 0 plus this is beta 1 into x1, first variable, right? So then beta 1 would be 2. Here you are getting 1.94. Again, a little bit variation is coming because of that noise term which you have added, right? Standard error in your coefficient measurement is 2.583. That means the actual coefficient can be 10.644 plus or minus 2.583. And similarly, actual coefficient x1 slope would be 1.9420 plus or minus 0.045. What is this T and all that we are going to discuss? What is omnibus? What is Q? What is kurtosis and all that we are going to do later on. Here, just for the sake of curiosity, if I remove this noise from my Y, then if I remove the noise, then I am taking a perfectly linear data set. And then if I print the result, you will see that R squared is now 100% and the coefficient R constant is equal to 10 because that was my 10, right? And slope is equal to 2. So the slope is equal to 2. So now I am at least mathematically able to explain that why that noise was added, because I don't want a perfectly linear distribution that you will rarely or almost never find this dotted line and on which these blue colored dots are there. That kind of this data points will never be found in practical data sets. So that's why I added some noise. Okay. Now I got this result. Now again I am getting the result with noise. So I got this result which is a fairly good linear model, 97.5 R square. Okay, in practical data set, if you get 97.5 R square, honestly, without overfitting, and honestly means without violating any basic tenets of data science, that is without overfitting and everything, then your boss will jump with joy from his chair, right? So this is a very good model. Now let us try to plot the data so that we understand more what this noise has done. Also, there is other reason for plotting that data. The other reason is that this discussion we started somewhere earlier. If you see, then when we are doing various applications of this that is part A of the chapter, implementing statistical calculation using SciPy and states model. And I said that these are various applications. This was our lecture 1. And I said that some of these applications we have already discussed, like this. Then this we are discussing, and all other applications we are going to take up in subsequent lecture. But in this ordinary least square regression, we have said that the regression can not only plot the line of best fit, but it can also provide diagnostic. Diagnostic means how good the model has fitted the data. So R squared is one important parameter, P values is another important parameter, confidence interval is another, and residual plots is another, right? So now I have just demonstrated R square, but now I want to demonstrate all these things also, that how from ordinary least square regression you can get P value, confidence interval, and residual plot. And for that, this plotting code is there. Now this code I myself wrote using this what you call AI coding tool, because otherwise it would be very difficult to obtain exactly perfect code which we needed to explain our point. So that is why if you don't get this code, or don't I mean cannot write such a code yourself, that you should not worry at all. Instead, you can just tell any AI coding model that I got this kind of data. Now help me with a code which can plot the line of best fit, and which can display confidence interval, which can display p-value, which can display the other thing was that critical value, okay, and maybe yes, that residuals, and it will plot the code for you. Okay, so now with AI assistance, things have become very easy. But let us plot it. Now this kind of plot is there. You can see that data points are just slightly scattered with respect to my this red colored line, and that is my line of best fit. Also, I get many important things. Blue colored are data points, red colored is the OLS regression line. The shaded pink color, that is the 5% confidence interval. We have done a detailed discussion on 5% confidence interval. So we know that that means the values I can say with 95% of the confidence that the predicted value will be in this pink shaded portion only every time I execute this linear model for this data set. So that means the model prediction may slightly vary. So this at present all predicted points are where on this red colored line, and blue are actual points, right? So that predicted point may shift a little bit here or a little bit below the red colored line, but they will never shift beyond this band, pink colored band. Okay, and that much can be said with 95% guarantee, or that is called 5% confidence interval. Right now, this is the actual data point is shown by blue, and the predicted data point for that is on this, and that is 89.91. That you can see actual is horizontally. If you draw one line, then its height is 106.29. Okay, it is above 100, and from this predicted data point, if you draw one horizontal line, then it is 89.9 or roughly 90. Okay, so from this, if I draw a line, then that is below 100 or 90. So actual value is more than the predicted value for this data point, which is above the line of fit, and that will be the same for all these data points also, because all these data points are above the line of fit. So for it, actual value will be more than the predicted value, or the error, that is predicted minus actual. Okay, or actual minus predicted, whatever you want to do, because in any case we are going to square it. So actual minus predicted, suppose we do, then the error for all points above the red colored line would be positive, but we are going to square it. Now here, this is one sample point given below the red colored line. Here actual value is always still on the red colored line only, and actual value comes out to be 49.89. Now what is that point? Then maybe from here somewhere, this is the actual value. Yeah, so this point, and if I draw horizontal line from it, then the line goes below 50, 49.89, right? And the predicted value will be where? Predicted value will be on the red colored line. Red colored line is itself the line passing through all predicted values. That is itself called the line of best fit, right? So then this is the predicted data point. Okay, and predicted value comes out to be 66.13. Is that clear? Okay, so in this case, actual is less and the predicted is more, and therefore the difference actual minus predicted, if you do, then the difference comes out to be 49.89 minus 66.13 negative, but again we are squaring it, so we get squared difference for these 2 points. One point is this lower point, its square difference is 263.64, and square difference for the upper point, that is this 106.29 minus 89.91 whole square, that is 268.24, like that. Similarly, we will find the squared difference, or which is also called squared errors, for all points, and then we will do the summation of it, addition of all those squared values, and then we will try to minimize it. When I say we will try to minimize it, we don't have to do anything. The algorithm itself finds this line such that the sum of squared error will be minimum for this line, for these data points, blue colored data points, right? Okay, now let us try to see various terms, that is called interpretation. Now this is the real important part, because I have seen many people who know everything, how to create OLS for their regression plot and everything, but they cannot, when they are asked about some things, they cannot explain what is the meaning of each term. Okay, so R squared is very common. Okay, first let us take each from here. So depth variable, so that is the dependent variable or response variable. Why? In the regression model. Then model, the term model, so that is which type of model you are using. So here it is ordinary least square model. Okay, so that is why it is OLS. Then method, then which method was used to fit the data. Obviously, if it is ordinary least square model, then the method used was least square. So that is what I said, that sum of squared errors were found, and such a line, red colored line, was obtained for which that sum of squared error is minimum. So a procedure which minimizes the sum square of residuals or difference between observed and actual value, that was adopted. Okay. Now number of observations. So number of observations is 50. That is because we created 50 observations in this case. Okay, but this output shows everything. Okay, so these are 50 observations that you can see here. Okay, then DF residuals, that is 48. Now what is DF? DF stands for degree of freedom of residuals. They are calculated as number of observations minus number of parameters which are being estimated. So what you are estimating, our equation, standard equation is beta 0 plus beta 1 into x1. So how many parameters you are estimating? Beta 0, that is the intercept term, and beta 1, that is the slope term, because this is a simple two-dimensional case. Okay. So then what is the degree of freedom? That degree of freedom is given as, for the residual, it is equal to total number of observations minus the number of unknowns which you are trying to find. So we are trying to find beta 0 and beta 1, or intercept and slope. So that is why it is 48. Degree of freedom of model. So this model, what is its degree of freedom? Which is the number of parameters only in the model, excluding the intercept. Parameters are what? That is number of observation. In previous case, degree of freedom of residuals, that is number of observations minus the number of parameters which are being estimated. While here, the degree of freedom of model, that is equal to number of parameters in the model, excluding the intercept, right? So number of parameters in the model are only two, beta 0 and beta 1. So among them also, beta 0 you have to exclude. So only one remains, beta 1. So what is the degree of freedom of model? Then 1. Okay. Covariance type is non-robust. Now that thing is that we saw that as x increases, as y also increases, and both have some positive correlation. So there is one term called correlation. Similarly, there is another term called covariance. That is, x varies in positive x direction, y also varies in positive y direction, and that covariance is, however, non-robust. So by default, OLS takes non-robust covariance only. It cannot take robust covariance, right? Okay. Then one more thing is this R squared. Now, what is R squared? It is an important parameter. It is a statistical measure of how close the data are to the fitted regression line. It is the proportion of variance in the dependent variable that is predictable from the independent variable, and a value of R square which is closer to 1 indicates a better fit. So it is a statistical measure of how good your best fit line is, because we have seen that the model tries to find the best possible, but best possible is not always workable. For example, here my model tried to find this in previous case. Yeah, here this line. Because that was the best possible it could do, but that best possible had only R squared 0.02, so that is only 0.2%. Then it is unacceptable. But here R square is 97.5%, so which is fairly good. So I can say that this red colored line, which is my model or line of best fit, that estimates how many percent of variance in y with change in x, then it explains 97.5% variation in y, okay, with variation in x. Now you read this again. Adjust R square is a statistical measure which shows how close the data are to the fitted regression line, and it is a proportion of variance in the dependent variable y that is predictable from the independent variable. So 97% of the dependent variable variance can be explained by using variance in x independent variable, and a value closer to 1 indicates better fit. So here the value is 9.975, means it is very good fit. Adjusted R square, adjust the R squared for the number of variables in the model. Okay, now this is again important thing, because sometimes, okay, you got R squared is equal to 0.975 for this model, but this was a very simple case in which there was only one independent variable, that is this x, or that means it is y is equal to beta 0 plus beta 1 x1 plus error term, right? Only that much. But the question is, suppose another data set is there, like this kind of data set, in which y is equal to beta 0 plus beta 1 x1 plus beta 2 x2, three-dimensionally distributed data points are there. Okay, now if I get R square is equal to, say, 0.96 for this data set, that is on the right side, that gray colored plane of best fit, I get 0.96. So should I say that for that linear model I got 0.975 here, and here I am getting 0.96? So should I say that this is a poor model? Now as far as R square is concerned, it shows that yes, this is better model. R square is equal to 0.975, and for the right side, that is two independent variables, R square is equal to 0.96. So it looks that yes, this is a better model than this. But can I actually compare apples with oranges like that? Because the problem here is only one independent variable was there. Here two independent variables are there. So if I want to compare this model with this model, there should be some parameter which adjusts for the number of the independent variables also. Because it should take into account that as the number of independent variables increases, the process of getting the line, or rather the plane of best fit, that is going to become more and more difficult. So this is not necessarily a poor model, because it has to do a difficult task, and still it is managing 96% of the R square. So there should be some parameter which takes into account this x1 and x2, how many independent variables are handled during the process. So that parameter is called adjusted R square. Now obviously in this case there is only one independent variable, so that is why R square and adjusted R square both are same. But if there are two independent variables, three independent variables, or if I am comparing two models, so at that time, at R square and adjusted R square, among them, adjusted R square is the really important quantity, right? Okay. Then F statistic measures the test. It is a measure which tests the overall significance of the regression model, and it compares the variance explained by the model with variance unexplained by the model. So here I get F statistic 1903. That means the ratio variance explained by the model divided by variance unexplained by the model is 1903. That is, it is like this: variance explained divided by variance unexplained is 1903, or in other words, variance explained is 1903 times variance which is unexplained, or that is nearly 2000 times the variance unexplained. So clearly that majority of the variance in my data is explained. Explained variance is 2000 times the unexplained variance. That is the measure, that the measure of that is given by F statistic. So F statistic is nearly 2000, which is, it should be as high as possible. Probability of F statistic should be low, and here it is coming out to be this much. Okay, so then probability of F statistic is the p-value corresponding to F statistic, and the low p-value indicates that the model provides good fit. Low is typically less than 0.05, but as I earlier also said, if it is healthcare or finance or that kind of critical application, then it can be less than 0.01 also. Now for our this model, we got 2.81 into x e to the power minus 20, or 2.81 10 to the power minus 40. Okay, so that is 0.000000 somewhere 39 zeros and then 281. So that is much less than even 0.01. So you can say that, you can say almost with 99.99% confidence that your model is highly accurately predicting the unknown variable y. Okay, then this log likelihood, which is the log of the likelihood function, which measures the goodness of the fit of the model, and higher the values of log likelihood indicates better model. So here I am getting log likelihood is equal to minus 1.181.27. Again, the value sign is not important, but this seems to be fairly high value, and that means that the model is fitting very well. AIC. Now AIC, or Akaike information criteria, that is also a measure of goodness of fit of the model, but its role is different. It is not the measure of goodness of fit in absolute terms, but whenever I have to compare two different models, at that time AIC becomes important. Okay, so it is the measure of relative quality of statistical model for a given set of data. AIC estimates the quality of each model relative to other model, and the formula for AIC is this: AIC is equal to 2k minus 2 times natural logarithm of L, where k is the number of parameters in the model and L is the likelihood of the model. Both these are already known from the earlier results. We have already found the likelihood, right? Log likelihood. So from which you can take anti-log and you can easily get the likelihood of the model. So that is not important, or actually here you require log likelihood only. So 2 times log likelihood. So then 2 times number of parameters minus 2 times log likelihood, that is equal to the AIC. Now that AIC has no specific value, so that you can say that this much AIC is good or this much AIC is bad for a given model, because AIC, its importance comes into picture when I am comparing this model with other OLS model. Now in OLS there is not much scope for say varying things, because this everything is decided by these lines, these 3 lines, right? Now there is no such thing as a hyperparameter and everything. So that is why one OLS and second OLS, that thing may not look very relevant to you. But in case of a random forest model, or in case of neural network, or in case of XGBoost, you can try many different things, because I told you that you can try 5 times 5-fold cross validation, but another person takes the same data, uses same algorithm, even same hyperparameters also, but he tries 10-fold cross validation, and now you want to compare model of first data scientist with model of second data scientist. Or it is possible that the first data scientist and second both have used XGBoost, both have used 10-fold cross validation only, but these have used the hyperparameters, say n1, n2 and n3, while this person has used some other hyperparameter values n1, n2 and n3, where there will be some numbers like that. Okay, so in that case, again I want to compare XGBoost model of the first data scientist with XGBoost model of second data scientist, then I have to look at AIC, and the real importance comes in this manner, right? So AIC rewards goodness of fit, but also includes a penalty, which is an increasing function of the number of estimated parameter, and therefore AIC discourages overfitting. So this is another important application, one important application of AIC I told you, to compare two models, right? And second important application is to decide when overfitting is occurring. Overfitting normally occurs when you take much complex model. For example, in that earlier chapter, we had seen this kind of example where crop yield depends upon the percentage cover. Then it also depends upon day length, average soil moisture, average maximum temperature, average minimum temperature, average air temperature, total rainfall, total radiation, time since last harvest, time since sown, and Julian day. So it is a perfect case for explaining what overfitting or when overfitting might occur. Okay, so in this kind of case, say this is the example for that overfitting case. In general, our linear model is y is equal to beta 0 plus beta 1 into x1 plus beta 2 x2 plus so on up to beta n into xn, where all these are features. So x1, x2. Now a given data set may have many features, but if you try to include all, then the model becomes very complex. The example was that only. Now here yield is my y and all these are x1, x2 up to xn. If I try to include all of them, then the model will become very complex. So what we try to do is, by that correlation analysis and something, we found that this average air temperature, average minimum temperature, average maximum temperature, these three are highly correlated, and therefore we can remove them. We can keep only one of them. Then we found that even average air temperature also is very poorly correlated, 0.06 correlation with my final yield y variable. So I decided to remove the even third also. That means everything related to the temperature we simply removed. Similarly, one was very poorly correlated, that is this 0.06. That was time since last harvest. So we could also remove that time since last harvest also. The why we are removing that? That was the question. Now the question is that the reason is that instead of making a model like y, suppose I take only two amongst these variables, two most important features. Suppose the most important features, and there are ways to find it. At present, don't bother from where I am getting it. But suppose I got that the most important feature is, say, this is the 0.65, the day length, and this, say, Julian day, or even that two are also highly correlated, Julian day and day length. So I can keep only one of them, but some other, say, 0.30, that is percentage cover and average soil moisture. These three are the most important features. So I am keeping among them these two first, day length and the percentage cover. Okay, and I make one model, and I get an AIC. Model means I'm trying to predict the yield using percentage cover and the day length, right? So x1 is equal to day length and x2 is equal to percentage cover, and I got the AIC for that model is 310. Okay, fine. Now then I found somewhere here that I included the third variable also. So percentage cover, day length, and average soil moisture. So the third one is also included in this manner, right? And I got the answer of yield, and the yield came out to be at that time 324. So sorry, not yield but AIC. AIC came out to be 324 for that model of estimating yield using percentage cover, moisture, and the third parameter was day length. Yeah, okay. So including those three as x1, x2, x3, I got a model, and that give me AIC 324. So that will tell me that I'm going on right track because my AIC increases. So here also I'm comparing two models, but one model with only two features and another model with three features, right? Okay. Then I added suppose some fourth feature, and any one, say this 0.19 is there, seems high correlation. So maybe I added that total radiation, or maybe I added total rainfall, any one. But when I added that fourth feature, so that means now y is equal to beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus beta 4 x4. Okay, n is equal to 4 independent variables. And in that case, I found AIC decreases. Then here I should be alarmed because AIC is a parameter which penalizes overfitting. So if AIC initially increase, so that means instead of two features, considering three features is better. But now instead of three, when I considered four features, then my AIC reduced. So that means that my overfitting is being penalized. So better would be to keep only three features. So AIC is a very important parameter in deciding when exactly overfitting is occurring. Okay, so here that is the exact sentence about that AIC. That here AIC rewards goodness of fit. So higher AIC is as such better. But it also includes a penalty, which is an increasing function of number of estimated parameters. And as a result, that penalty discourages overfitting. So as a result, what happens if AIC decreases, then that means that penalty is now coming into picture, and you have to stop adding the feature, because data science is much of an empirical science. So whenever multiple features are there, like this example, then we try all features. But how to try all features? So we take the yield y, and we first keep only one feature, then keep 1 and 2, then keep 1, 2 and 3, then keep 1, 2, 3, 4 like that. And as we go on adding the number of features, you have to keep an eye on AIC for each model which is being created. Then if the model with two features gives this AIC, model with these three features gives this AIC, so that means adding the third feature was worthwhile because AIC should be higher. But if adding the fourth feature suddenly reduce my AIC, so that means that fourth feature should not be added because it is leading to overfitting, and therefore I should not use it. Okay. So that is one important thing about this AIC, right? Now, about these other parameters, BIC and all that, we will discuss in the next lecture. Thank you.